So today what I want to do is another kind of divide and conquer. We're going to see the same paradigm of a recursive divide and conquer algorithm. We'll do a similar kind of style of analysis of setting up the recurrence relation, solving the recurrence relation. And this is going to be a more, well, a non-trivial algorithm, one that surprised people when it was first seen. And this is going to be a deterministic worst case analysis. And later we'll also see a randomized version of this, one where it'll be easy to see that on average, in expectation, the algorithm runs fast, but the algorithm itself is a little bit easier. So that's one of the things I'm trying to incorporate into this version of 222, which we haven't done so much in the past, is this course in 122 has almost always in the past been about deterministic algorithms. And increasingly people are understanding that randomized algorithms can give you the same expected time bounds, not worst case time bounds, and run very effectively in practice and are oftentimes much simpler. So I want to try to give you illustrations of that. But today what we're going to talk about is median finding. So the median, you're given a set. Let's say x1 through xn of n numbers. And this is unsorted, of course. And the problem is find the median number in the set. Well, the median, that's the number such that half the elements are less than it and half are bigger than it. And under that definition, there's one extra. We have more than 100%. Anyway, half the elements roughly are less than it, and half roughly are larger than it. And of course, if the number of elements is odd, then I could have the same number which are less as are larger. If the number of elements is even, then we have to decide. There are actually two medians, or we have to decide which median we're talking about. Okay, so everybody knows what a median is. Now, what's the simplest way you know of to find the median of n numbers? Sorted. Sorted. Yeah, you could sort the numbers in n log n time with an algorithm which runs in big O of n log n operations. And then once you have the sorted list, you just find the median element. Again, if it's an odd number of elements, you know exactly which element we're talking about. And if it's even number, then there are two. And it was thought, I don't know, until the early 70s, I guess, that that was probably the best you could do. People knew that you couldn't sort better than in the comparison-based model, which we'll talk about later. You couldn't sort with an algorithm whose worst case behavior was better than n log n. And the assumption was that that would also be true for median, because median sounded like it was so related to sorting. And then people found an algorithm whose worst case running time is not n log n to find the median, but it's just order n. It's time proportional to the number of elements you can find the median. You don't actually have to sort. You can do something else. And that came as a big surprise to people. Since then, there are lots of different ways of doing it. I think what I'm going to show you is pretty close to the original method that was given. And so here it is. Actually, this is called the Big Five method, because a whole bunch of people were standing out in front of that sporting goods. No, it's five particular famous people who either were famous then or became famous since then, partly because of this. And so here's the way this goes. You divide your numbers. Let's just, for simplicity, assume that n is a multiple of 5. Okay, in the book, they treat a more general case, and they're going to come out with some small change elements into the analysis that you may not see here because they don't make that assumption. But actually, you'll see, for the most cleanliness, we would actually like it to be a power of 5, but that's a little too restrictive. But assume n is some multiple of 5. So in the first step, what we're going to do is just arbitrarily divide the set into groups of 5 elements. And I'm going to draw this pictorially like this: 3, 4, 5. 1, 2, 3, 4, 5, and so on. So these are groups of 5. Then we're going to find the median of each group of 5. Well, first of all, how much time does it take to do this division into groups of 5? Well, that's really a low-level question depending on how you've represented it. But certainly, if you did it in some way that took you more than order n, you're working too hard on making this slow. But how much time does it take you to find the median of each group? Well, OK, but the way I phrased the question was how much time does it take for each group, for a single group? Just constant time. 5 is a constant number. It's a fixed number. You can dream up all kinds of algorithms that will find the median of 5 numbers. And each one of them takes some fixed number of operations. So that's just a constant. And that's usually written order 1 per group. And so order n overall. OK? So I'm carrying along the time analysis as I'm doing the algorithm as well. Then we want to find the median of the n over 5 medians. So I've got one median from each one of these groups of 5. And that gives me a set of n over 5 elements, and I can find the median of those, which I do obviously recursively, because n over 5 is not a constant number. So I'm going to do that recursively. And if T of n is going to denote the total number of operations, this is going to take T of n over 5 operations. Okay. I can't read my own writing. And we'll let x, maybe x star, denote that median of medians. Step 4, find more boardroom. Well, now we compare x star with every element, or every number, to find the numbers smaller than x star, and those larger than x star. Okay, now I have to actually go back to the beginning and make a slight, not a correction, but a modification, which is that what I'm showing you now is the recursive algorithm for finding the ith smallest element. So it's a greater generality. And when we call this to find the median, our first call of this is to set I equal to n over 2. And then this will work. But the recursive call, which I'm coming to next, is going to be using this changing I. Okay? So this is the algorithm to find the ith smallest element. Okay. So, by the way, in this step, how much time does this step take? Or event. It's just a direct compare of all the elements to this median of medians. And that's, you'll see now why I need this to be general. So let's let K, let's give a name to these sets. Find the number smaller than x star, and that's called set A. And those that are larger than x star, and call that set B. Okay? Let K be the size of set A. And I should have given a name to this algorithm. So this is called select I. Okay? So select I on set A if K, well, if what? What's the relationship between K and I? What? Yeah, if K is greater than I, or greater than or equal. I'm in this select where I'm trying to find the ith smallest, and I found an element, x star, and I found that there's a whole bunch of elements that are smaller than x star. In fact, there's more of those than I. There's k of them, and k is bigger than or equal to I. So, and I know that the other ones are all bigger than x star. So where's the ith smallest? It's in set A. So you want to recurse on set A, finding the ith smallest. Otherwise, maybe I should, instead of saying use, I just say recurse, or call. Otherwise, you recurse on select of what? Yeah, you've got k of them, I minus k. I guess there's some, so what do we want to do with x star? X star, we know, well, the simplest thing is just assume that all the numbers are distinct. And then I'm off the hook. If you're actually programming this thing, then you're going to have to worry about the possibility of ties. And then you have to worry about the possibility of that x star is the ith smallest. Okay. But let's just assume no ties. And so you want to select on I minus k on set B. Oh, actually, sorry. I minus k plus 1, if I'm assuming they're all distinct. There are k which were less than x star, and there's x star which is assumed and this is if k was strictly less than I. I guess there is one, if I've assumed that they're all distinct, there's one other possibility, isn't there? On the assumption that they're all distinct, there is the possibility that x star was the ith smallest. And you would see that if k was I minus 1. Okay? Those guys are all strictly smaller than x star. The other ones are all strictly bigger. And so the ith smallest is just I itself. Yeah, is x star.
It would be I minus k minus 1 on the last leg because x star is neither an A nor B.
Thank you. And then if k equals I minus 1, then we return x star. So this is a classic kind of divide and conquer. You've partitioned the elements into two sets, A and B, and then you're going to recurse on the appropriate one of those. There's the possibility that you have what you wanted in hand, that's the x star, and that's in fact how you terminate. That's your return condition. Okay. There's another condition, or another termination condition, which is when the size of the set that you're working on gets small enough, then you just move over to some algorithm that definitely finds the median. I mean, we could set that wherever you like. I think actually what the book says for that analysis is when the size of the set falls below 80, you assume, or 20, or so, whatever number you really want to make up, you assume that you go over to some canned algorithm which works for sets of that size. You don't keep calling the recursion when the size of the set gets to be too small. It's just not profitable. And it makes the analysis more difficult, which I think why they cut off at 80 for this exposition. All right. Clear to everybody? Now let me ask one question here. If the size of A and the size of B were roughly equal each time, then can you see what the overall running time would be like? You should see that it would be big O of n pretty easily, because if we're separating the original set into two roughly equal sized sets, and we're only working on one of them, that's different than the way merge sort went. That's different than the way the lower envelope went. In that divide and conquer, you had to work on both sides. But in this, once you've separated the two sets, once you found the two sets, you're only working on one side or the other. So if they're of size roughly a half each, then you're only going to work on half at each level of recursion. And then the recurrence relation would be like this. T of n would be T of n over 2. That's the recursive part, plus something which is big O of n. That was all the other stuff in there. Oh, we do have this T of n over 5. Okay. Well, what do you think is the relationship? Oh, I see. Okay, maybe it shouldn't be so obvious at this moment. We'll do the analysis and you'll see it. Yeah?
Will the analysis explain what's so magical about the number 5?
No. The question was, what's so magical about the number 5? And the answer is, other numbers will work, but not all so easily. Okay, 5 is a nice number for the analysis. And some other numbers actually don't work very well. It makes the analysis really ugly or not working. Okay, but now this idea that we're going to roughly select half at each level of recursion, there's no reason to believe that. We don't have any guarantee yet that that's going to happen, that it's going to split roughly in half. Okay, so we can't just assume that's going to happen. We have to look more carefully at the specifics of the algorithm to see what's the biggest set we could possibly have when we do that recursion. So let's try to look at that. So here I have, let's say I've written this out now, so these are all the medians. Of the individual sets of 5. And then 1, 2, 3, 4, 5, 6. Let's just put another one in here. And imagine that this is the median of the medians. So this is our x star right here. And these, therefore, and I've written them so that these are all less than this x star, and these are all larger than the x star. Now, what else can we say about the other elements in here? Oh, and let's also, this is small to large, and this way is small to large. With that picture, there are certain implications that we can see. These elements above here are smaller than this one, and this is smaller than that one. So these guys up here are all smaller than that one as well. Right? Question? Comment? No? Okay, so these guys up here, those are all strictly... Sorry, what? Yeah, right. So in each column, we have these sorted, displayed anyway. And remember, the algorithm isn't sorting these, but I get to display this as a for purposes of explanation. So I've displayed these this way. And then small to large, that's the way I've arranged the medians. Okay. So in here, each element that I've written above here is smaller than its respective median, which is smaller than this x star. So these guys are all less than x star. And the same reasoning leads you to see, since these guys are bigger than x star, and each one in their column is bigger than it, that these are greater than x star. Okay? And these guys here are also bigger than x star. So I should have folded that in. And these are all less than x star. That should be folded into there as well. Okay? So we actually get to, we get to know that. And of course, since the algorithm in... Yeah.
Is that true? Saying that in the second set of 5, you have an infinity up there, just some very large value. But its median value, looking at the vertical second set, but its median value is, you know, whatever, it's 1. That infinity is certainly not smaller. The median is 1. That set belongs in the position that it is when you sort small to large, but that infinity is certainly not smaller than the median of the median.
Where do you want infinity? Which?
Upper right of your circle, or either one.
You want this to be infinity?
Right there.
Okay, but then it's not small. Okay.
Right.
I'm displaying these sorted small to large, although the algorithm isn't actually finding them sorted. Okay, so that infinity would go down here. Okay, all right. So if we know for sure that there's some set here which is strictly less than x star, and there's some other set here which is of elements which is strictly larger than x star, okay, the question is this: what's the largest size question? What is the largest that set A could be? Well, or equivalently B. It's the same symmetric for B. Okay? Set A, remember, making the camera operator do a lot of work here, and probably people in Livermore are getting dizzy. But, sorry. We want to know what's the largest that set A, the small guys, could be. And you can see it can't be the same, it can't be as big as n, it can't be the entire set we started from, because we have a group of elements here which are guaranteed to be strictly bigger than x star. So how big is this set in here? What's the size of this set in here? Well, here we have to be careful to have constants. We can't just say order n. We need some. It's what? Yeah, it looks roughly like a quarter of n. Okay, I'm going to do this a little bit more, carefully. So here's our set B. The elements in here are, well, it looks like about half of the columns are contained here. So that's, they're n over 5 columns, so about n over 10. And it looks like we get 3 elements in here per column. So that's about 3n over 10. And we actually get this little extra bit here, which is a 2. Okay, and so I'd like to say that B is about 3n over 10. We know that B is, I should conclude B is greater than or equal to 3n over 10, which means that the biggest that A can be is about 7n over 10. Okay? So now the book actually says 7n over 10 plus 6. Okay? And where do they get that extra 6? It partly has to do with the fact that they haven't assumed that n is divisible by 5. So there's some little extras which are, for worst case, going to throw on the other side, maybe up to 3 of them. And there's some things in x's. Well, when I said that the columns that we were considering there were about half of the columns, well, they want to say it's about half rounded down. So they're being a little bit more careful, and they're getting an extra 6 here. All right, but it isn't going to matter. So I'm just going to say about 7n over 10. Yeah?
Could you explain again how you get 7n over 10?
Okay. Yeah, the crucial thing was, okay, that question over there is framed as what's the biggest that set A could be? And I looked at the converse set B and implicitly asked, how big is B at least? And then I take what I know about how big B is at least, and I subtract that from n. And then I get the answer to that one. So these guys in this circle here, this weird circle, we already concluded that these had to be strictly bigger than x star. So they're not in A. They're in B. Now, some other stuff could be in B too. We don't know. Some stuff up here could be in B. Some stuff over here could be in B. Okay? We don't know where this stuff goes, A or B. But we just concluded that this in here is in B, and so it can't be in A. And now I'm just estimating, well, how many elements is this? And I said initially, well, it's about half of the n over 5 columns. So it's about n over 10 columns. And in each column, we're getting 3 elements. So in fact, really, well, so I'm being a little sloppy because I've forgotten this thing in here, and is n really divisible by 5, et cetera, all those little small change issues. Did that make more sense? And then when you subtract 3n over 10 from n, you get 7n over 10.
Also, that 3 and that 10 is only good for 5 for the divisions of 5.
Well, certainly if we had divided into groups of size 26, say, instead of size 5, the analysis would be different. We'd have n over 26 sets. et cetera. And yeah, so that's that 5, which leads to a 10, which leads to this 10, is very much tied to the algorithm, definitely.
What the advantage of this algorithm? It seems that the complexity of by using this algorithm is even worse than using sorting. Kind of.
You're asking why would I use this algorithm?
Yeah, it seems that this algorithm is no better than the sorting one.
But the question is this algorithm any better? Well, we haven't finished the analysis, but when we finish the analysis and we see that the total number of operations here grows as order n, and we're sorting, and remember this is a whole worst case viewpoint. In worst case viewpoint, in sorting, that grows as n log n. N log n grows faster than n. Okay, so we have an algorithm which in worst case, in terms of its worst case growth function, is faster. That definitely we should all understand once I finish the analysis. Okay, now if you're asking a bigger philosophical question, or actually an engineering question, of which one should you use if you want to find the median, should you use a sorting method or should you use this particular median method, then that's a much more that's a much more open question, and you can try that with experiments, and expected time is a much more relevant question than worst case time. Okay, but we look at these kind of algorithms for if only, even if they're not necessarily practical, if only for the surprise value, because we should be surprised that you can find the median with a worst case running time which is asymptotically smaller than what it takes to sort. That was a big surprise in the field and is kind of a wake up for our intuition. But if you were just asking about whether this is going to, in worst case, be better than sorting, well, just wait 5 minutes and we'll have done the analysis. Okay, so how big can A be? About 7n over 10. All right, and from that, we can set up our recurrence. T of n, let's just go through all the steps. I hope I haven't erased the important ones. We have big O of n steps that take big O of n time. And then we have a step here which takes t n over 5. So we've got to throw that in the recurrence. And then we have another step which takes, well, how much time does step 5 take? It takes what? Well, that's the size of the set. Yeah, so this takes time. So step 5 takes time, t 7n over 10, because that is the biggest that the set could be. And the analysis for B was the same as the analysis for A. That's the biggest that set could be when we do this recursive call. So T of n is equal to some big O(n) term. And I'm going to actually write down a constant here. We don't know what it is, but I'm going to keep alive this just in terms to help me do the analysis. I'm actually going to write down something here. Plus T of n over 5 plus T of 7n over 10.
And the largest set of B is also 7 over 10. So the largest set of B is also 7 over 10.
Right. Yeah. The analysis we did for set A is the same is symmetric to the analysis we should be doing for set B, but it's the same. And the key thing here is that we don't put 2 here because this recursion only works on one side or the other. Right, so we only have this 7n over 10 once, not twice. Page 6. All right. Now, how do we solve this? We want to get a closed form solution for T of n. And this is actually where it's a little bit simpler rather than discovering the closed form solution either by unwrapping or by other analytical tools. We're just going to cheat. When you know or when you've guessed what the solution to a recurrence relation is with closed form solution, you can verify it by substitution. You plug it in, you see if you actually get an equality. Okay, so I'm going to tell you what we think T of n is, plug it in on here, do some simplifications, and see that in fact you get an equality. All right. Now, as I was saying earlier, the algorithm they're really telling you to do is this. When the size of the set gets below 80, just move to some other algorithm. 80 is a finite number, and so whatever algorithm you use is going to have some finite number of operations, and that's just theta of 1. That 80 is a kind of a magic, you'll see where that number falls out from, why they wanted that when we get there. And I will observe this, that 7 over n over 10, actually plus 6, which is what the book is carrying along, is less than or equal to n for, actually it's n, it's certainly true for n greater than or equal to 80. It's actually, isn't it true, I think, for n greater than or equal to 20? So certainly true for n greater than or equal to 80. Okay, actually, now let me, what do I want? Let me put a little prime here, okay? Just so I'm consistent with my notes. So here's the claim. There exists some constant c such that T of n is less than or equal to c times n. In other words, T of n is big O of n. Okay, so I have to, this is my claimed solution, and this is what I'm going to substitute in for T of n. Some constant, which I don't yet know, times n. And you see why I wanted to change this to a different symbol, because this constant here on this number of operations may not, is unrelated initially to c. We're going to establish a relationship later, but anyway, it's certainly not necessarily the same. Okay, so let's just do some plug and chug. So here's our claim. Again, after substitution, T of n is less than or equal to I'll carry along. I never assumed that n was a power of 5. So eventually, even if I started with something that was a multiple of 5, we're going to get down to something where this is not a whole number. So just put that in there. 7n over 10. Let me just carry along the 6. We were saying it's the size of A that we're recursing on is at most 7n over 10. So certainly it's less than or equal to 7n over 10 plus 6. But now I'm being consistent with my notes, which is consistent with the book. And I know from 20 years of experience that when I try to change these things in mid-lecture, I get screwed up. So I better follow my notes, plus C prime n. That's the work that was done before the recursions. This was the median of medians, and this is the recursion on set A or set B. All right. Next step is trivial. We're going to get rid of this upper brackets, Cn over 5. I'll do that by just adding in another C. Can't hurt. Plus 7Cn over 10. This is all just manipulation, but 6C plus, then there's the C prime n. And this is less than or equal, clean this stuff up. 9Cn over 10 plus 7C plus C prime n. Now, we're trying to show this claim by substitution. Substitution, I just substituted for T of n, I just substituted C times n, and we got this business. I'm not done until I show that this is less than or equal to C times n. So less than or equal to Cn, that has to be written with a question mark because I haven't. If I just wrote this down now, that would be a proof by magic. Okay? We do have to say something about this and why it's less than or equal to C times n. Well, it depends on what C and C prime are. You can certainly pick C and C primes so that this is not going to be true. But the key is going to be that for every C prime, and assuming that n is bigger than 80, there will be an n, there will be a C, which makes this true. Okay, so let's just clean this up just one more step. So if we want this to be true, then we need C prime n less than or equal to 1/10 Cn minus 7C. Or, according to my notes, Cn over 10 minus 7 greater than or equal to C prime. Right? That's what we need. We need to pick a C and a C prime such that this is true, and remembering that the algorithm moves to something else when n is less than 80. So here's where the 80 came out of. This thing is greater than 1, or greater than or equal to 1, for n greater than or equal to 80. So all I have to do, so just pick C to be, well, I'll make it even strictly bigger. Somebody's going to ask me if I don't. Greater than or equal to C prime. Whatever the C prime is that came from all the other work, the non-recursive work in the algorithm, just make C that size or bigger. And then everything works out. And we have shown that T of n is big O of n. The punchline, though, the moral punchline, is we have a method now that finds the median of n numbers in a number of operations, which is big O of n. But to sort, the best we have is an algorithm whose number of operations is big O of n log n. So we definitely have something which is, at least in worst case sense, asymptotic worst case sense, superior to sorting. And that came as a big surprise. Now, just actually as a sort of a lead into something else I'm going to talk about today or next time, this algorithm has running time big O of n. Can I say yet that it has running time theta of n?
choice that you do, and then you're define that. But you can make a lower bound as the amount of work that you have to do.
Well, what I'm trying to point out is, in this case, the lower bound is lower bounding of this amount is very simple. Yeah, you want
To be correct about finding the median, you have to inspect at least all numbers you got. So you have at least a runtime of n no matter what you do.
Okay, so there are two approaches. One is to look at the specific algorithm and notice that in this specific algorithm, it has a step at the top of the recursion where it's looking at every number. Okay, it's comparing every number to the x star, for example. So with respect to that single algorithm, it's very simple to say its running time is omega of n. And since we now have that it's big O of n and it's omega of n, therefore it's theta of n. I'm just completing in this case, a trivial, but completing the lower bound analysis for that specific algorithm. Now, what was also suggested was that we can make an argument that any algorithm that finds the median must look at every element in the set. And you can try to formalize that by a method that we are going to discuss called the adversary method, where you imagine that you have an algorithm which didn't do that. There's some element out there that it never looked at. And yet it comes to conclude, the algorithm comes to conclude what the median is. And let's just say that the number of elements is odd, so the median, and they're all distinct, so the median is unique. So this algorithm is happily concluding that it has the median, but it never looked at, there's some particular element it never looked at. And so what the adversary does is looks at the output that the algorithm came up with, and then decides on the value of the element it didn't look at in order to make the algorithm wrong. Should the median, should that element it didn't look at be bigger or smaller than the element it thought was the median? Okay, that's a very simple case of the adversary argument, which shows that any algorithm that finds a median must, in worst case, look at every element. And we're going to prove a higher lower bound for median finding based on adversary arguments as well. It probably won't be today, but it'll be next time.